In this tutorial, we extend the idea of the free-falling object from 1D to 2D. So if we look at the previous free fall, um, we just drop it from a certain height and this object just keeps falling. And you know that if this object had some x component of the velocity as well, it will follow a projectile motion. Um, so in this tutorial, we will derive that, or we will solve that problem with some x velocity given as well. So in this case, um, you can think of the same equation that we had for 1D case, where we had just second derivative with respect to y. You can think of a vector which is a position of the object, and a vector derivative, second order derivative, and in this case we have mg, where g is the gravitational acceleration, and in our problem we know there is no x direction, there's only a y direction, which is minus 9.8. So this potentially are two equations, that there is no acceleration in the x direction, but there is acceleration in the y direction, which is equal to mg. And so in order to convert this vector second order differential equation to two first order differential equations, we can define u and v as x and y components of the velocity, and define a v vector which has both of these components in it. And then if we look at these two second order differential equations, they both can be converted into each into two single or first order differential equations. So this one becomes dx over dt is equal to u, which is the velocity, and then du over dt, which is the acceleration, is equal to 0. And for the second case, we have dy by dt is equal to the vertical velocity v, and then dv by dt is equal to mg. So we have converted this second order vector differential equation into four first order differential equations. And as we talked about this in the class, now we have a system of equations. Our goal is to find x and y and u and v. And so we create a state matrix, which is x, y, u, v, and then a function, which is the slope function, which we get from the other side of these equations. So we have u, v, 0, and mg. So that's our slope function. And we also have our initial conditions. So we know that the object is initially at 0, 0 location and moving in the x direction at 5 meters per second, and in the y direction with 40 meters per second. So now we can make an initial vector for the state, which is x0, y0, u0, and v0, and in our case it's 0, 0, 5, and 40. So again, as you can see, this boils down to implementation of the Euler's equation. So if I know the previous state of the object, I can find its new state by using the slope function and time increment. As you can see, this is a very easy implementation because you have done it so many times for scalar quantities. And then in the last tutorial, we also did it for a vector quantity. So we just need to extend this idea of creating a state vector and initial state vector that we did in the last lab. So for this purpose, let's start by again having our parameters. So here is at time is equal to 0, the initial state vector is 0, 0, 5, 40. That's the one what we saw earlier. Again, we create a time domain. In this case, we're going to go all the way to 20 seconds with a dt of 0.1 seconds, and we're going to create our time array and state array to hold all the information. And now you can see that I am creating n by 4 state arrays. So each row of this will contain a value of the state x, y, u, v at various time steps. Okay, and then in the update part, we basically just say our new value of the state variable is the old value of the state variable plus phi times delta t. Phi times delta t. And we know that phi is u, v, 0, and mg. So uv is coming from the state array or state vector. It's the third and fourth value, and then 0 and mg. So as you can see here, I'm using the state vector's third value from the previous time step and the fourth value from the previous time step, 0 and mg. Okay, so this is my Euler's implementation. And again, I'm setting these boundary conditions. So I'm saying if I reach the x boundary, then just reverse the x direction of the object, and if I hit the ground, then make it 50% return velocity. So there is it's an inelastic collision, and there is some loss in the velocity, and then the rest is the visualization that you already know before. So we are putting, this is the location of the current location of the object, and this I'm plotting it as a line to show the trajectory of the object. So this will show you in green color what path the object has followed, and then this at each point, current point, it also makes a vector showing us which way the object is moving and what is the speed of the object. So if we run this code, we will see that now we are moving up with 40 and sideways with 5, and you can see now it's going to start, it's a 2D object, and the motion is two-dimensional, and this is where the velocity, return velocity, is 50%. So this tutorial demonstrates that you can very easily take any differential equation, whether it's scalar or vector, and convert it into several first order differential equations, so which results in a system of differential equations, and then that system can be converted into a state, an Euler methods implementation, where we are just updating a state vector at each time step, and this way we can solve the original differential equation that we were required to solve. Okay. So in the next tutorial, we'll also include the drag into this free fall object.